Girls, I am Shamsunisa from Royal Degree College, Chemistry Department. As we are seeing about third unit physical chemistry, in that chemical kinetics, today we are going to study about methods of determining order of a reaction, problems, and kinetics of complex reactions. First of all, we'll see about methods of determining order of a reaction. Order of a reaction can be determined by following methods. First one is integration method or trial method. In this method, the reaction is carried out with known quantities of reactants and the concentration of reactants at different time intervals is determined by simple experiment. These values are substituted in integrated rate equation for first, second order reaction, etc. You can see here K1 it is equal to, that is the rate constant for the first order reaction. The expression is K1 equal to 2.303 by T log A by A minus X. Rate constant for the second order reaction, the equation will be like this: K2 equal to 1 by T into 1 by A minus X minus 1 by A. Then rate constant for the third order reaction, equation will be like this: K3 equal to 1 by 2T into 1 by A minus X whole square minus 1 by A square. The equation which gives constant value of K, the rate constant indicate the appropriate order. Alternatively, the validity of the various rate equations can be tested by graphical method. First one is log A minus X versus time. It will give a straight line for first order reaction. 1 by A minus X versus time, it will give a straight line for second order. But this method is not useful for fractional order reactions. Second method we will see, that is half-life method for the determination of order of a reaction. Half-life period of different order reactions are: for the first order reaction, half-life period is T half equal to 0.693 by K1. For second order reaction, half-life period is T half equal to 1 by K2A. For third order reaction, half-life is inversely proportional to A square. That is, T half is inversely proportional to A square. By observing the above equations, it can be known that half-life period for first order reaction is independent of initial concentration. Here you can see initial concentration is not there in the first order reaction. Means it is independent of initial concentration, and that for the second order is inversely proportional to initial concentration. Thus we can write general relation between half-life period and initial concentration as T half, it is inversely proportional to 1 by A to the power n minus 1, where n is called the order of reaction and A is the initial concentration. By carrying out the reaction with two different initial concentrations A1 and A2 and finding out half-life period in case of T1 and T2, the order of reaction can be determined as, here you can see T1, it is inversely proportional to A1 to the power n minus 1. T2 is inversely proportional to 1 by A2 to the power n minus 1. We are dividing these equations, so next equation will be T1 by T2. See here, it is equal to A2 by A1 to the power n minus 1. So T1, T2 are half-life period for different concentrations A1 and A2. So T1 by T2 it is equal to A2 by A1 to the power n minus 1. Applying log on both sides. So we can write the equation like this: log T1 by T2 it is equal to log A2 by A1 to the power n minus 1. Now we are using this formula. Log A to the power m, it is equal to m log A. Okay, so n minus 1 is nothing but m. It will come before log. Okay, so like this we are writing here in the next equation, n minus 1 log a2 by a1. Then this log a2 by a1 we are bringing to the other side. So we can write in this way, log t1 by t2 it is divided by log a2 by a1 equal to n minus 1. Now this one we are bringing to the other side. Minus 1 will become plus 1. So like this we are getting the equation. Now we are using this particular equation here. Log a by b it is equal to log a minus log b. So this log t1 by t2 is nothing but a divided by a2. This formula log a by b it is equal to log a minus log b. This is we are applying on this, that is log t1. T1 is a by t2 is b. Like that a2 is what a2 is a and a1 is b. So we can write the equation like this, log t1 minus log t2 divided by log a minus log a2 minus log a1 plus 1 as it is equal to n. So we can write in this way also, n equal to 1 plus log t1 minus log t2 divided by log a2 minus log a1. Here n is called what? Order of reaction. And this particular equation, it is used to calculate the order of reaction by Hoff-like method. Next method we will see, that is named as Van 't Hoff differential method to determine the order of reaction. In general, rate of reaction varies as nth power of concentration in rate equation. So we can write like this, rate of the reaction R it is equal to dx by dt, that is change in concentration of X divided by change in time. It is equal to k c to the power n. So R is nothing but now R is equal to k c to the power n. In case of dx by dt we are writing k c to the power n. So R is equal to k c to the power n. For C1 and C2 concentrations, R1 and R2 are the rate constant. Means for C1 concentration rate of the reaction is R1. For C2 concentration rate of the reaction is R2. So R1 it is equal to K C1 to the power n, and then R2 equal to K C2 to the power n. Applying log on both sides. So we can write like this, log R1 equal to log K C1 to the power n, then log R2 equal to log K C2 to the power n. Now we are using this formula, log AB it is equal to log A plus log B. So log A, this K is A and C1 square is B. Okay, so we are writing like this, log R1 it is equal to log K plus log C1 square. Like that we are writing for the another. Look at this particular first equation, after applying the log on both sides, we are getting these two equations. Now, these two equations we are writing in this form. That is log AB it is equal to log A plus log B. Okay. So here in the first equation, log K is there, that is nothing but A. Then C1 to the power n is B, log B. So we are writing like this, log R1 it is equal to log K plus log C1 to the power n. Then the next equation like that only we are writing, that is log R2 it is equal to log K plus log C2 to the power n. Now we are applying this formula, that is log A to the power m it is equal to m log A. Okay, this n we are writing before log A. So we will get like this, log R1 it is equal to log K plus n log C1. It is our equation number 1. Like that only we are writing second equation, log R2 it is equal to log K plus n log C2. It is our equation number 2. Subtracting equation 1 from equation 2. So we are writing the equation 2 first, that is log R2 it is equal to log K plus n log C2, and then we are writing equation number 1, log R1 it is equal to log K plus n log C1. Okay, we are subtracting here. If the positive sign is there, at that time we are writing here negative value. We are changing here the sign of equation 1. Okay, here the positive sign is there, so that's why we are converting it into negative. Okay, if the negative will be there, at that time it will become positive, but here we are subtracting, so the negative. So now this Plus log k minus log k gets cancelled. Then rest of the things we are writing like this: log R2, then minus this minus log R1. It is equal to n log C2, then minus n log C1. So this will n here we are taking n as common. So the rest of the things are as it is, and we are taking as common log C2 minus log C1 we are writing. Now this log C2 minus log C1 we are bringing to the other side, so it will come in the denominator. Then log R2 minus log R1 divided by log C2 minus log C1, it is equal to n. Or we can write in this way also, that is n equal to log R2 minus log R1 divided by log C2 minus log C1. N is what? N is nothing but order of reaction. This method involves determination of concentration of the reactants at different time intervals. Then the values of R1 and R2 are evaluated by plotting concentration and time graph corresponding to the two different concentrations C1 and C2. Substituting all these values in the above equation, we will get order of reaction. That is, n value we can find out. Next method we will see to evaluate or to determine the order of reaction, that is named as Oswald isolation method. This method is applicable for reactions involving two or more reactants. In this method, the experiment is carried out for a number of times, each time taking all the reactants in excess except one reactant turn by turn. So the reactant which is not taken in excess, which is in small quantity, is said to be isolated. It is known that the one which is taken in excess will not affect the rate of reaction. Thus, the kinetics of the reaction then gives the order of reaction with respect to the isolated reactant. So, the order found for the different reactants are then added up to get overall order of reaction. We are adding the values. So, consider a reaction here involving how many reactants? 3 reactants. One is X plus Y and third one is Z. These 3 reactants are reacting, and as a result of that we are getting the products. Let the order of the reaction be N1. When the order of the reaction will be N1? When X is isolated. And X is isolated, that is Y and Z are taken in excess. Y and Z are taken in excess. Like that, similarly, N2 is the order of reaction when Y is isolated. So when Y is isolated, X and Z are taken in excess quantity. Then if the order of the reaction will be N3, at that time Z will be isolated and X and Y will be taken in large excess quantity. Thus overall order of the reaction will be N1 plus N2 plus N3. Now we will see the problems. First problem, when the concentration of the reactant is increased from 0.2 m to 0.5 m, half-life period decreased from 25 minutes to 4 minutes. Calculate the order of reaction. So the given data is T1. T1 is what? The half-life period. Half-life period, the first half-life period is 25 minutes. From 25 minutes, it is decreasing to 4 minutes. That is second half-life period T2 is 4 minutes. Then initial concentration of one of the reactant is 0.2 m, and for the second reactant, initial concentration is 0.5 m. Now we are using this formula, and it is equal to 1 plus log T1 by T2 divided by log A2 by A1. In place of T1, T2, we are substituting its values. T1 value is 25 divided by T2 value is 4, and then log A2 value is 0.5 divided by A1 value is 0.2. Now separately we are doing the calculation. We are taking first of all log 25 by 4. Then we are simplifying this. Log 5 square. 5 square means 5 into 5. 5 5 is 25 will get again. Then the 2 is square. 2 2s are 4 we will get. Then this Both of them they are showing the square na. So whole square we can write log 5 by 2 whole square. Then we are using this formula log a to the power m, it is equal to m log a. That is 2 we are bringing before log 5 by 2. So log 5 by 2 whole square, it is equal to 2 log 5 by 2. Next, this part we are simplifying now. That is log 0 0.5 by 0 0.2. Point gets cancelled. So we will get the value as log 5 by 2. Then these value we are substituting in that equation. So n it is equal to 1 plus 2 log 5 by 2 divided by log 5 by 2. Log 5 by 2 log 5 by 2 gets cancelled. So n equal to 1 plus 2 it is nothing but 3. So the order of the reaction will be 3. Third order reaction you can say. Second problem we will see half-life of a chemical reaction at particular concentration is 50 minutes. When the concentration is doubled, the half-life becomes 100 minutes. Find out the order of reaction. So the given data is here. T1 is how much? 50 minutes. T2 is 100 minutes. A initial concentration. A1 is A. And then the next initial concentration will be what? Initial concentration becoming double. Concentration is double. So A2 value will be 2A. Now we are using this formula. T1 by T2 it is equal to A2 by A1 to the power n minus 1. In case of T1 we are substituting its value 50 by T2 value is 100. It is equal to A2 value is 2A divided by A1 value is A. So A gets cancelled. 0 0 gets cancelled. 5 ones are 5. 5 twos are 10. So you will get 1 by 2. It is equal to 2 to the power n minus 1. Now 1 by 2, like this also we can write 1 by 2, it is nothing but the 2 will go to the numerator, so it will become 2 to the power minus 1 we can write. It is equal to 2 to the power n minus 1. If bases are equal, see here, both the bases are equal, then powers can be equated. So minus 1 it is equal to n minus 1. Then minus 1 as it is, this minus 1 we are bringing to other side, plus 1 it will become equal to n, plus minus 1 gets cancelled, so n equal to 0. So this is the zero order reaction. Next, the third problem we'll see, consider the following data for a reaction. Find the order of a reaction. See the table here, initial pressure. If the initial pressure is 707, half-life is 84. Initial pressure is 500, half-life is 83.8. Initial pressure 79, half-life is 84. Then initial pressure 37.5, half-life is 83.5. So here is asking to calculate again the order of reaction. So from the data, it can be known that half-life is independent of initial concentration. It is not at all dependent on the initial concentration. It is not given here. So the reaction is first order. Pressure can be taken in place of concentration. So the given data will be like this. T1 value is 84 and T2 value is 83.8. Then A1 value, in place of concentration we are taking here pressure value. A1 is 707 and A2 is 500. Now we are using this formula T1 by T2 equal to A2 by A1 to the power n minus 1. Now we are substituting the values. T1 value is 84 divided by T2 value is 83.8. It is equal to A2 value is 500 divided by A1 value is 707 to the power n minus 1. Then 84 divided by 83.8 means round figure we are taking as 84. It is equal to, if we are dividing 500 by 707 means we will get the value as 0.7 to the power n minus 1. Then here 84 gets cancelled, we will get 1 to the power 0. It is equal to 0.7 means we can take the value as 1. It is 1 to the power now n minus 1. Here also, if the bases are equal, powers can be equated. So 0 it is equal to n minus 1. So 1, this minus 1 we are bringing to the other side, so it will become the plus 1. So 1 equal to n, it is nothing but n equal to 1. That is order of the reaction is first order reaction. Now we'll see about the kinetics of complex reactions. It involves 2 or 3 different elementary steps at the same time, so that the mathematical description of overall reaction cannot be governed by simple integrated rate equations like first order reaction, second order reaction or third order reactions. But it will be the resultant of several different rate expressions. Such type of complex reactions are classified into four categories. First one is opposing reaction, second is consecutive reactions, third is parallel reactions, and the fourth one is chain reactions. All these are the four types of complex reactions. Now we'll see about the opposing reactions. What is this? The reactions in which the products of a chemical change react back to form the original reactant. Means once the reactants are reacting, we are getting the product. When we are getting the product, when the products will react with one another, we are getting back the reactant. So this type of reaction is called opposing reaction or counter reaction or reversible reaction. In opposing reactions, both forward and backward reactions takes place and attain equilibrium after some time. So the net rate of reaction will be influenced by both the forward and as well as backward rates. Thus causes a serious disturbance in the measurement of reaction rates. Consider here a reaction for which both the forward and backward reactions are of first order. Here you can see the reaction. From the reactant A, at the rate constant K1, we are getting the product B. And from the product B, at the rate constant K2, we are getting the reactant A. Again, we are getting that. So the forward and the backward reaction are taking place here. So initial concentration of capital A is small a and initial concentration of capital B is 0. After time T, concentration of B is X and concentration of capital A is A minus X. So K1 is what? It is nothing but first order rate constant for forward reaction. And K2 is the first order rate constant for backward reaction. Now the rate of forward reaction, it is equal to K1 A minus X. Rate of backward reaction is K2 X. So the net rate of the production of B is dx by dt, that is change in the concentration of X with respect to time. It is equal to K1 A minus X minus K2 X. It is our equation number 1. At equilibrium, the net rate is 0. That is, net rate is 0 means dx by dt it is equal to 0. So it is nothing but, therefore we can say K1 A minus Xe minus K2 Xe, it is equal to 0. What is Xe? Xe is the equilibrium concentration. So here in this case, dx by dt, it is becoming 0 here. So we can see this equation now, that is this one, the K1 A minus Xe minus K2 Xe, it is equal to 0. So next the K1, see here, K1 A minus Xe, it is as it is equal to minus K2 Xe, we are bringing to the other side. So it will become plus. Then K2 Xe, it is equal to K1 X minus Xe, like this also we can write. Now this Xe we are bringing to the other side, so it will go to the denominator. K2 will remain there. K2 it is equal to K1 A minus Xe divided by Xe. It is our equation number 2. So substituting the value of K2 from equation 2 in 1 we get. So we can see this is our equation number 1. dx by dt it is equal to K1 A minus X minus K2 X. Isn't it? So in place of K2, we are substituting the value of K2 from equation 2nd. So already we have substituted here. X as it is we are writing. Then the next step is this, we are opening this one. That is K1 into A, K1A. Then minus K1 into X, K1 X. Minus, see here, K1 into A into X. So K1 AX by Xe. And then K1 into Xe into X divided by X. So now here Xe gets cancelled. So we will get this step. That is here remains what? K1x will remain here. How? Look at this once again, girls. Look at this once again. Look at this equation. From this we are taking K1a common. See here, K1a and here also K1a. We are taking K1a as common. If the K1 is A is going outside, as we are taking it as a common, here nothing is there, we are writing here 1. Then minus. Then here remains what? X. This X we are writing. Nothing is there below 1 means here we can write 1. So here x by xe as it is we are writing. Then minus we are taking this k1x. K1x. This minus K1x we are taking, then plus K1x. So now the minus K1x plus K1x gets cancelled. Here, as you can see, xe into 1. So you will get here xe. Then 1 into x divided by xe. So in the next step, dx by dt it is equal to K1a by xe into xe minus x. So dx by dt it is equal to k1a into xe minus x by xe. As we got this equation, this xe minus x we are bringing to the other side and dt we are bringing to this side, right side. So we will get this equation dx by xe minus x it is equal to k1a dt by xe. Now integrating on both sides. So integration dx by xe minus x it is equal to integration k1a dt by xe. Now we are using this formula. Integration of 1 by x dx it is equal to minus ln x and integration of dx equal to x. So integration of dx by xe minus x it is nothing but equal to minus ln xe minus x. It is equal to now the k1a by xe it is constant. So we are writing as it is. Integration of dt equal to t plus c we are writing because the c is integration constant. It is our equation number 3. So at t equal to 0, x equal to 0. In place of t, in place of x, we are keeping 0 in that equation. So we'll get like this equation minus log xe minus 0. It is equal to k1a into 0 by xe plus c. So in place of time, we are writing 0 and in place of x, we are keeping the value as 0. So now what remains in the next step? Minus ln xe. It is equal to c because k1a by xe into 0, it will become 0. So we'll get here only c. It is our equation number 4. This is the value of c we got here. So substituting equation 4 in equation 3. So we are taking equation 3 main. In equation 3 in place of c. See, in the equation 3, c we are writing here. That is integration constant. In place of c, we are keeping the value of c as minus ln xe. Look at this equation. Then in the next step, what we are doing, this one plus into minus will become minus. The rest of the things are as it is here. Next, in the next step, this minus ln xe we are bringing to the other side. So it will become plus ln xe. This is as it is we are copying minus ln xe minus x. It is equal to k1a t by xe. Now in the next step, what we are doing, this x we are bringing to the other side and at we are bringing to this side, left hand side. Okay. So the xe will go to the numerator. Xe into ln xe minus ln xe minus x divided by at, it is equal to what? K1. Since log a minus log b, it is equal to log a by b. So we are writing like this, xe by at log xe by xe minus x, it is equal to K1. So examples we are seeing here, the first example is alpha glucose at the rate constant K1 converted to beta glucose, and beta glucose product at the rate constant K2. From this we are getting back the reactant, that is alpha glucose. It is the best example of a reversible first order reaction. Second example is conversion of ammonium cyanide to urea. See, NH4CNO is ammonium cyanide. It is converted to urea, NH2CO, NH2. And the urea, from urea again we are getting back the reactant, that is ammonium cyanide. Both are the examples of reversible first order reaction. Second reaction we will see now, that is consecutive reactions. Chemical reactions which proceed from reactants to product through one or more intermediate stages are called consecutive reactions. These reactions are very common in polymerization and depolymerization processes. For these reactions, the rate constant is being determined by such a stage which is the slowest state. Consider here the following consecutive reaction in which both stages are of first order. Look at this. From the reactant A, at the rate constant K1, we are getting the product B. And from the product B at the rate constant K2, we are getting the product C. So here the intermediate reactant is here B and A is the main reactant. From that we are getting the final product as C. Let A be the initial concentration of capital A. Initial concentration of capital A is small a at the time 0 and the concentration of B is 0 and concentration of C will be 0. And after the time t, concentration of A will be x, concentration of B will be y, and the concentration of C will be z. Thus we can write like this: x plus y plus z, it is equal to A. The rate of disappearance of A, it is equal to dx by dt. It is equal to what? K1 molar concentration of A. Then what is the concentration of A? That is x after the time t, isn't it? So dx by dt it is equal to k1x. It is our equation number 1. Then the rate of formation of B is equal to dy by dt. Change in the concentration of Y with respect to time. It is equal to k1x minus k2y. It is our equation number 6. Now rate of formation of C, that is equal to dz by dt. It is equal to k2z. It is our equation number 3. Now from equation 1, 2 and 3 we get x equal to ae to the power minus k1t, y it is equal to k1a by k2 minus k1 into e to the power minus k1t minus e to the power minus k2t. We know x plus y plus z, it is equal to a, isn't it? So z we are keeping this side only, okay, then it is equal to a is that side only, and x we are bringing to the other side, it will become minus x, y we are bringing to the other side, y will become minus y. So the value of z is, what is the value of z? So in the next step, in place of a, we are writing the value of a, means as it is we are writing this a, then minus x value we are writing this x value a e to the power minus k1t, and minus y value we are writing, that is k1a into e to the power minus k1t minus e to the power minus k2t by k2 minus k1, that we are writing. Nothing is there below a and this value means we can keep 1 here. So now this k2 minus k1 into a, so we can write k2 minus k1 a, then minus this k2 minus k1 into ae to the power minus k1t, that one we are writing, then minus this is as it is, we are getting k1 a e to the power minus k1t minus e to the power minus k2t. So now divided by k2 minus k1. Now in the next step, what we are doing here, a see, here A is there, here A and here A. We are keeping A as common and we are taking it outside. A by K2 minus K1. Then we are writing this K2 minus K1, then minus K2. This one we are opening. It is multiplied with this. K2 AE. A we are not writing. Why? Because we are already taken the A as common. So K2 e to the power minus K1t. Then again we are writing here minus into minus plus, then k1, okay, k1 e to the power minus k1t, that one. Then here this one, the plus into minus, again it will become minus. Here this one as it is we are keeping, first of all minus k1 e to the power minus k1t, then minus into minus plus, then K1 e to the power minus K2 t. This one we are writing. Now this, the positive and negative same values, they are going to be cancelled. That is plus K1 e to the power minus K1 t minus K2 to the power K1 K2 e to the power minus K1 t. Both values gets cancelled. Rest of the things are as it is. We are keeping as it is. But here now what we are doing, we are bringing K2 to one side. See the next step. K2, then this K2 we are writing, then minus K2 e to the power minus K1t, that we are writing. Then this minus we are keeping. Then here K1 we are bringing to the same side. That is K1, then minus K1 e to the power minus K2t. That one we are writing. So from these equations, the concentration changes of A, B and C with time t of reaction can be graphically represented. See here, from the graph, it can be observed that the concentration of A falls continuously. See, concentration of A falls continuously, then the concentration of C rises continuously, and the concentration of B rises to maximum, then decreases with time. Next, we will see the examples of consecutive reactions. First example is hydrolysis of ester. Here we are taking diethyl succinate. It is ester. It occurs in two stages. First of all, we are taking diethyl succinate. In the presence of acid, hydrolysis reaction will take place. Water we are adding in that. So what will happen from this side? C2H5, it is coming out, reacting with OH of the water molecule, and we are getting the side product as ethyl alcohol. And this hydrogen from water molecule, it is substituted in place of ethyl group. So we are getting this compound. Next is, as we are getting this product now, that we are taking as a reactant in the next step. In the presence of acid, again hydrolysis reaction will take place in this. From this side, C2H5 coming out, reacting with OH of water molecule, and we are getting ethyl alcohol. And in place of C2H5, here one hydrogen from water molecule is substituted, and we are getting this acid which is named as succinic acid. Next example we'll see of ethylene glycol converted to glyoxal. How? This is the ethylene glycol, CH2OH, single bond CH2OH. From that H2, it is coming out from this side. These two hydrogen atoms are coming out. So as this H2 is coming out from this side, this OH, it is turning and attaching to the carbon as CHO. CHO, single bond CH2OH. Okay, this is the product we got here, which is nothing but intermediate unstable compound also we can say. So in that, from this particular intermediate compound, again H2 is coming out, see, from this side, and this OH, it is turning and attaching to the carbon as CHO. CHO, single bond CHO. We are getting here the glyoxal. Now the third type of the reaction we will see, that is the parallel reactions. The reactions in which the reacting substances, instead of proceeding along one path to yield the products, also follows two or more paths to give different products, are called parallel reactions. See here, A reacted by following one path. From that we are getting the product B, 90% product will get. And if A reactant will follow the second path, we are getting the product C. This product percentage is 10%. So A is the reactant which undergoes the two reactions here, the first and the second. If it is undergoing the first reaction, we are getting the product B, and if it is undergoing the second reaction, we are getting the product C. So the reaction first is known as main reaction, and the second is known as side reaction or parallel reaction. Examples of parallel reactions we will see. When ethyl alcohol is made to react, the following side reactions along with the main reaction may occur. See here, we are taking ethyl alcohol at the rate constant K1, we are getting these two products, that is C2H4 ethylene along with water molecule. This is our main reaction. And from ethyl alcohol only, at the rate constant K2, we are getting acetaldehyde along with hydrogen. And from ethyl alcohol only at the rate constant K3 we are getting the product diethyl ether and water molecule. So these two reactions we can say are considered as the parallel reaction, and the first reaction will be a main reaction or main product we are getting in that reaction. Now another example we'll see, we are taking the phenol. In that we are adding nitric acid, HNO3. We are expanding that one and we are writing that one as HONO2. In the presence of sulfuric acid, the reaction will take place at the rate constant K1. So what will happen, from the para position of the phenol, one hydrogen is coming out reacting with OH of the nitric acid, and we are getting the side product as water molecule, and in place of that para position hydrogen atom, NO2 is substituted there, so we are getting as a para-nitrophenol. Okay. Next is, from the phenol, if we are adding the nitric acid in that and sulfuric acid at the rate constant K2, so what will happen, at the ortho position, one hydrogen you can represent here outside the benzene ring. That hydrogen will come out reacting with OH of the nitric acid, and we are getting the side product H2O, and in place of ortho hydrogen, NO2 is substituted, so it is named as orthonitrophenol. So one reaction, that is the first reaction is the main reaction, and the second reaction what we are seeing here, that is in which we are getting the product as orthonitrophenol. This is the parallel reaction, you can say. Mathematical treatment of parallel reaction. Now we will talk about this. Consider the reaction A. At the rate constant K1 we are getting the product B. This is the first part. Then the second part is, from the reactant A at the rate constant K2 we are getting the product C. Suppose A is the initial concentration, small a is the initial concentration of reactant A. Then X is the amount of A decomposed in the time T to form partly B and partly as C. So if Y and Z are the amounts of B and C, Y is the amount of B and C is and the amount of C is Z after the time T. Here you can see A. Actually, initial concentration of capital A is small a, initial concentration of capital B is 0, and the initial concentration of C is 0. Okay. At the time T, concentration of C is A minus X, concentration of B is A minus X, and concentration of A will be minus A minus X. Why? Because rate of disappearance of A we are seeing here. That is equal to minus dx by dt. It is disappearing. As a result of that, the formation of B and C products will take place. So here, rate of disappearance of A is equal to minus dx by dt. Then rate of formation of B and C together, it is equal to dx by dt. That is plus dx by dt. We are adding B and C. Then rate of, if we are seeing separately, rate of formation of B and rate of formation of C. So the rate of formation of B is equal to dy by dt. That is change in the concentration of Y with respect to time. That is the rate of formation of B. And rate of formation of C is dz by dt. Since both B and C are formed from A, we can write like this. That is dx by dt, it is equal to B plus C, isn't it? So now we are writing the value of B. B value is dy by dt plus C value is dz by dt. It is our equation number 1. If the reaction is first order and K1 is the rate constant for the formation of B from A, then dy by dt, it is equal to K1 A minus X. It is equation number 2. Then the rate of formation of C is given by, rate of formation of C is Z dz by dt, isn't it? It is given as like this, dz by dt it is equal to K2 A minus X. It is our equation number 3. K2 is what? Rate constant for the formation of C. And K1 is rate constant for the formation of B. Substituting equation 2 and 3 in equation 1. So we get dx by dt, it is equal to what is equation 2? See here. Equation 2 and equation 3 values we are substituting in first equation. In place of dy by dt, we are substituting this value k1 a minus x. Okay. Then plus equation third is dz by dt is equal to k2 a minus x. So in place of c, we are keeping in place of c or in place of dz by dt, we are keeping its value as k2 a minus x. See, like this we got this equation. Then dx by dt, it is equal to, see here, a minus x we are taking as common. Then k1 plus k2 we are getting. Then here k1 plus k2, since k1 plus k2 it is equal to k. So in place of k1 plus k2 we can write k. Now this a minus x we are bringing to the other side and dt we are bringing to right hand side. So dx by d a minus x, it is equal to k dt. Now integrating on both sides. So integration of dx by a minus x, it is equal to integration k dt. Now we are using this formula, integration of 1 by a minus x dx, it is equal to log a by a minus x. And integration of dt we know it is equal to t, isn't it? So now we are taking in place of integration dx by a minus x, we are writing log a by a minus x. It is equal to k is the constant, so as it is we are writing integration of dt is t, so we are writing kt. Now this t we are bringing to the other side. So 1 by t we are writing log a by a minus x is equal to k. Or we can write like this also. Both are same, that is k equal to 1 by t log a by a minus x. It is our equation number 4. Now we can see, in order to evaluate k1 and k2 separately, we must know some relationship between them. The amounts of B and C formed at any time will depend upon the rate of the two reactions. That is, amount of B at any stage, that is nothing but dy by dt. It should be divided by amount of C at any stage, dz by dt. So in place of dy by dt, we are keeping the value of dy by dt, that is k1 a minus x. Then in place of dz by dt, we are keeping its value as k2 a minus x. Now a minus x gets cancelled, so we will get k1 by k2. k1 by k2, that is equal to k dash. It is our equation number 5. So the values of k1 and k2 can be calculated separately from equation 4 and 5 in terms of k and k dash, which are directly measurable quantities. Now we'll see the derivation of k2. k1 plus k2, it is equal to k. We know this. It is our equation number 4. Then k1 by k2 equal to k dash. It is equation 5. Then this one k1, it is equal to k1, it is equal to k dash k2. Okay. See, look at this equation, equation 5. From that we are getting equation 6. How? This k2 we are bringing to the other side. So k dash k2, it is equal to what? K1. This is our equation number 6. Substituting k1 in equation 4. We are taking equation 4 mean in place of k1, we are substituting its value. What is the value of k1? Just now we got in equation 6, k dash k2, that we are writing plus k2 as it is equal to k. So k2 we are taking as common. So here k2 into k dash plus 1. Then this one k dash plus 1 we are bringing to the other side. So k by 1 plus k dash, it is equal to k2. Now the value of k2 is derived. Now we will see about the derivation of k1. We are writing this equation 4 as it is k1 plus k2, it is equal to k, and k1 it is equal to k dash k2, it is our equation number 6. From this particular equation, k dash we are bringing to the other side. So k1 by k dash, it will be equal to k2. Substituting k2 in equation 4 now. So the k, it is equal to k1 as it is we are writing plus k2. In place of k2 we are writing the k2 value as k1 k dash. So now k1 by 1 we are writing. Why? Because in the denominator nothing is there, means we can write 1. Now k dash into k1 k dash plus 1 into k1 by k dash. So now k1 we are taking as common. What remains here? K dash plus 1. So divided by k dash. Now this particular k, this value whole k dash plus 1 we are bringing to the other side, and this k dash we are bringing to the other side. Okay, so k dash divided by k dash plus k1, it is equal to k1. So we have derived this value of k. Now we'll see the last reaction, that is the chain reaction. Photochemical reactions proceed continuously as long as the reacting substances are present in the reaction. The mechanism of chain reaction involves three steps. They are: first step is chain initiation step, second one is chain propagation step, and third one is chain termination step. Now we can see the example. Photochemical reaction between H2 and Cl2 to form HCl. The mechanism is given as. See here, we are taking the chlorine molecule in the presence of light. That is a photochemical reaction which takes place here, and as a result of that, we are getting that 2 moles of chlorine free radical reference. Chain initiation steps. Now, as we are getting the chlorine free radical, it will react with hydrogen H2, and as a result of that, we are getting HCl plus hydrogen free radical. Then that hydrogen free radical, it will react with the chlorine, and as a result of that we are getting HCl and chlorine free radical. These two steps are considered to be as the chain propagation steps. So here H dot and Cl dot, they are nothing but the hydrogen and chlorine free radical. They are chain carriers. So chlorine free radical plus chlorine free radical, when they will combine, and as a result of that we are getting the chlorine molecule. With this, the chain will stop. That is chain termination step. This one. Thank you for listening my lecture, guys.